So the need for big data processing keeps growing, and the space has been evolving steadily for the last couple of decades. This talk is an exploration to see where we can potentially go next. Um, these are the three major models that we use for processing big data: batch, streaming, and scatter gather. The objective of this talk is to see if we can simplify this to two models, streaming 2.0 and scatter gather. The basic idea behind streaming 2.0 is that it's an evolution of streaming, which accommodates for all the offline use cases for which we use batch processing today. And it has to be able to do it efficiently and scalably. I'd like to start this discussion with defining the core difference between batch and streaming, because it forms the foundation of much of the content that's about to be discussed. And although this topic has been touched upon in many places, I feel that often the core point is missed. So to illustrate the fundamental difference between these two models, I'd like to illustrate this using this a simple job, which we will run it through the batch model as well as the streaming model and see how they differ. In the batch model, it doesn't matter what engine we are specifically using, whether it's Flink batch or Spark batch or Hive or something else. The essence of the execution is the same. In the batch mode, the first stage will be spun up. So there's only one stage running at a time. So let's say if you were to assign 4 containers to the batch job, stage 1 will spin up on these 4 containers and it will swallow all of the inputs from wherever it's supposed to read it and dump it to a collection of disks spread over a few hosts. Once it's done, it basically dies, the stage, and then the stage 2 is spun up on another 4 containers, and that will consume the output of stage 1 and then produce the output to disks again. And finally, stage 2 also disappears and stage 3 comes up, and the same cycle repeats for all the downstream stages. That's the basic lifestyle of a batch job. The key observation here is there's only one stage running at a time, and the output of the stages is buffered. With streaming, all the stages will be running concurrently as opposed to one at a time. So what that means is stage 1 and stage 2 can communicate directly without an intermediate buffering the space. This means much faster communication. You get better throughput, significantly good throughput, and also latency wise. So this kind of communication is really fast and cheap. Cheap because you don't have to spend the extra dollars on those disks to buffer those outputs. So in that case, what do we think of a single stage job? Is that a streaming job or a batch job? And the answer is, it doesn't matter. You can call it whatever and you would be right. So for example, if you have a single stage job running under Flink streaming and a single stage job running under Spark batch, they are fundamentally same as long as they're doing the same compute. There's no fundamental difference between the two. So to summarize, batch execution is one stage at a time and the outputs are buffered. With streaming execution, the stages are pipelined. The observation being made here is also that in streaming, there is a flexibility that the operators have with respect to when they produce the outputs. So they could be producing outputs continuously or periodically, or something similar to batch jobs. They could just produce the data at the outputs at the very end in case of a bounded input. There are a few common beliefs being noted here that are generally not true. It is often regarded that if you have some bounded data or some offline data, batch is the way to go. And if if you are dealing with unbounded data or real-time data, you are basically that's the only time you want to use streaming. The truth is that streaming can actually handle both bounded as well as unbounded data, and later on in this talk we'll also see that it can do it very efficiently. Also, there's no reason to believe that you cannot use streaming for ad hoc jobs or some kind of a periodic execution of a job, like a daily, some kind of a end of the day kind of a this thing, if necessary. It just, it doesn't have to be batch. Streaming, there's some belief that streaming reads versus batch reads are somewhat fundamentally different. But actually, a streaming source or a batch source, either way, once it starts reading from its input, it's going to keep reading till the input is exhausted. At a fundamental level, they have access to the same APIs and able to do pretty much anything that each other can do. These are some popular streaming engines. They're largely used on the real-time use cases, things like Flink, Storm, and so forth. But there's another class of engines called as MPP databases, which are often considered as batch style execution. But when you look into them, they're actually using pipeline executions under the scenes. So they're not actually batch engines, but they're streaming engines, which are specialized to deal with bounded data. So they have more optimized processing of bounded data. So you can think of these MPP engines on the right as offline streaming engines, whereas the engines on the left, they're basically real-time streaming engines. But both are streaming. The real-time streaming engines have certain primitives to deal with, event time and more specialized for unbounded data, which is often seen in real time. Just decoupling some concepts here, because they're often used interchangeably sometimes, and that can lead to confusing situations. So in this talk, we'll be largely referring to offline and real time, where it implies the freshness of the data being consumed. Batch and streaming is basically the execution model or the processing model. And bounded, unbounded refers to the finiteness of the data. Coming to the word batch, this word has different meanings based on the context it's being used. In the world of batch processing, it can mean the size of the input given to a job. And microbatching means you're dividing that larger input into smaller batches and running it through multiple executions of the job. The Spark streaming uses microbatching, but fundamentally, microbatching is not pipeline execution, which means microbatching cannot be called streaming. In the world of stream processing, the word batch may refer to, for example, the buffer size is being used to exchange between operators. Or it could also mean the size of the input in case it's a bounded input. The word microbatch in the world of stream processing also has another meaning, which is used by Apache Storm with its Trident API. They're referring to the boundaries in a stream on which they provide exactly one's guarantees. So in Storm, microbatch is still pure streaming. It's not actually a batch execution. There are additional meanings for the word batch, which can lead to additional ambiguity and faulty inferencing. For example, the word could mean an offline use case, it could mean bounded data, it could mean batch processing, it could mean periodic execution as well. So for example, somebody may say, we have batch data in Hive, and therefore we need batch processing. If that phrasing is changed to we have a batch of data, then that could actually imply that you could either use batch processing or stream processing. And in fact, in many of these cases, they are using stream processing just through MPP databases. Another example is when somebody says, we have a batch workload. What they're really saying is that they have an offline use case, or they want to run some job periodically. And of course, for these use cases as well, you could use either batch or streaming. There are some myths around streaming being covered here. So a common belief is that stream processing cannot exploit metadata or indexes or optimized algorithms that process bounded data. Or another belief is that you can do columnar formats or vectorized execution in streaming, or it's not suited for periodic processing. But again, MPP engines have been doing this with streaming in streaming mode for a long time now. So clearly, these are not limitations of stream processing. Another myth is that if you reduce the batch size for batch job, then you get stream processing. But regardless of how small you get with the batch size, micro batching will never be streaming just because it's never pipeline execution. So even at micro batch size equal to 1, it's still not streaming. In this section, I will dig into why streaming has an advantage over batch with respect to throughput, latency, as well as scale. The throughput and latency part should be more obvious because, as we've seen before, there is no need to buffer the outputs in streaming, and therefore the data can move through the stages much quicker. In fact, data can move through the stages in a matter of milliseconds because it's not sitting in some buffers. So you get better throughput as well as latency. Also, as a side effect of the pipeline execution, you have the ability to have incremental results and not have to wait for the job to complete. The impact of scale may not be so obvious and therefore may be more interesting. There are two things that impact scale, and the first one is output buffering. In the case of batch, again, because these disks are basically buffering all of the outputs from stage 1, they have to kind of be scaled as the size of the input to the batch job increases. So for example, if you feed 10 terabytes there, you may have to collect 10 terabytes out of the stage 1 as well, and similarly downstream. Whereas if you're constantly draining, you are eliminated the need to linearly scale or keep increasing the size of these disks to accommodate larger and larger inputs. So this basically makes it for much better scaling. This property where you don't need to add more and more resources to handle larger and larger inputs is referred to as optional scaling. And it's a property we'll discuss a little bit later on. But now let's turn our attention to the second thing that impacts scale, which is state. So state is something that's maintained by each operator in the job. And there's stateful operators and there's stateless operators. So in this example here, we have filter operator in stage 1, which is basically a stateless operator. And similarly, the transform operator in stage 3 is also stateless. Whereas the sum operator in the second stage is it's a stateful operator. It needs to maintain some kind of a count. So if it's a word count, for example, it's going to have a hash map with the words and the counts for each word. So a state is something that's maintained at each stage, and it's separate from the output. The state is mutable, whereas outputs are immutable. The interesting thing about state with respect to scale is that you need to budget for it. You need to potentially add more and more resources if the amount of state keeps increasing with the input size. And this is true both in terms of streaming as well as batch. Now, there's an interesting thing that real-time streaming engines do, which offline streaming engines as well as batch do not seem to be exploiting, which is periodic flushing of state that if the input data has some order available, typically event time based ordering. And what that means is if you can flush out the state, for example, if you're doing hourly counts and you start seeing the next hour's count, you can flush all the state for the previous hour. So that keeps the amount of state very low. So you don't have to hold on to all the counts for the entire history. And this is a very interesting property with respect to scale. Let's now take a concrete example of an offline job and do some back of the envelope calculations to assess the difference in resource requirements for a batch job versus a streaming job to understand the impact of scale. And I'm kind of taking a little bit of an extreme example in which is considered to favor batch mode conventionally, which is a fact table join. So we are basically joining two bounded inputs, a large size, and we're going to compare how much resources it requires in batch mode versus streaming mode. In the batch mode, let's say we have this job graph. These are the two sources. Each one is basically being fed 1 terabyte of data from the fact table. And then it will basically reshuffle the data and produce 1 terabyte each, totaling up to 2 terabytes. So it's essentially just made a repartitioned copy of the input on disk here. And then that's fed into the stage 3, which will start sorting the partitioned data. And let's say it requires 1 terabyte on each side to do the sorting in an array list. So that's another 2 terabytes here. And then it produces the sorted output, which is 2 terabytes. And that's fed to stage 4. So in this case, we have a total of 6 terabytes required. So that's the 2 terabytes of state here, plus the output, the 2 terabytes. And it also needs to kind of hold on to the input till it produces the output. So the total requirements is about 6 terabytes. On the streaming mode, let's say you feed 1 terabyte each on the fact tables, and that translates to 1 terabyte required to sort the data in memory, same as batch mode, but we've eliminated the disk. So the total requirement in this case is just 2 terabytes. So you can see there's a significant difference in terms of resources required between batch versus streaming. And obviously this is proportional to the input size. So as the input size grows, this amount of space required also grows, and it doesn't grow as fast in the streaming mode as in the batch mode. So let's simplify this example where if you assume the input is already partitioned, then you can eliminate the first stage and you can merge that sources directly into the downstream stage and sort it without having to repartition it. So in this case, if you feed that 1 terabyte each directly to the sort as it is pre-partitioned, then the 1 terabyte and 1 terabyte is required for the sorting, and then the merge join will basically write the output, these merged joined output to disk, and this basically translates to 4 terabytes. In the streaming mode, there is no change here. It's still 2 terabytes because there is the amount of state stays the same. Now we can further simplify this example by assuming that the input is already sorted and partitioned, and therefore what it means is you can eliminate the sort step within this stage here. And in this case, This translates to 2 terabytes of space in the batch example and 0 in the case of the streaming example. So the summary is that when you estimate space, you need to accommodate for the output size plus the state size in batch jobs. In streaming jobs, it's just the state sizes. And by and large, you will see that streaming jobs are require less resources, even for offline jobs. And here, I'm not even considering all the periodic flushing of states and such optimizations in more advanced cases, which are normally only done by streaming engines. If offline streaming is more scalable than batch, then why are MPP databases not considered to be as scalable as batch systems is a question that's worth answering. In my view, there's 2 issues which limit the scalability of MPP databases. One has to do with the fact that they tend to hold the state in memory. They don't allow it to be spilled over to disk and stuff like that, as we can do in Flink by using RocksDB as the state backend. Now, Presto seems to be experimenting with this feature, enabling this feature, but I believe it's probably operator specific and may not be released as yet. The second, the point here is that MPP databases have a fixed number of containers pre-launched and multiple jobs are being launched on the same set of containers. So there's sharing of containers between jobs and these jobs are being preempted. So there's preemptive scheduling going on there. So this also limits the scalability because they're sharing CPU and memory. But as you can see, neither of these are fundamental limitations of the streaming model. They're just primarily design choices or implementation limitations. Let's talk about optional scaling, a term that I briefly introduced in an earlier slide. In distributed computing, we've gone through those phases of vertical and horizontal scaling where you would either have to add more powerful machines to keep up with the scale or the job would fail, or the alternative was to add more machines to keep up with the scale or the job would fail. So the term optional scaling is primarily recognizing that there is a subset of jobs or use cases which don't actually need to be given more and more resources in order to handle larger and larger inputs. Basically, if you give them some amount of estimated resources, then they're able to process essentially infinite amounts of data with just that amount of resources. The word optional there simply means that adding more resources is optional, and that's something you may want to do if you want to, say, speed up the job, but it's not something you're forced to do to handle larger inputs. This basically means larger jobs are able to run with smaller footprints. If you think about it, the real-time streaming jobs have been doing this for a long time now. You launch a streaming job, let's say with 4 or 10 or whatever containers, and day after day for months, they're processing, endless amounts of data, and then they keep going. So this is an interesting property, which is worth recognizing. It usually applies to jobs which have a fixed amount of state size and something that does not change with the input size. This next slide is taken from the Kappa Plus architecture presentation. It introduces a framework on how to think about classifying operators based on their state requirements, because it's very useful to have something like this to estimate your job's resource requirements. And that's very useful when you're thinking in terms of scale. the this system, this categorization system, basically talks about the stateful and the stateless operators, and then there's a so category 1 is stateless operators, category 2, 3, and 4 are stateful. For category 2 here is the lightweight state. Category 3 is significantly larger, and 4 is extraordinarily large. Category 2 is operators like sum, min, max, average, counts, and so forth. If you think of an example where you're trying to count the number of rides that are happening in a given city, you just have, the amount of state limited to the number of cities multiplied by the bytes required to maintain the count. And that's not a whole lot. The category 3 is much larger. Here, it involves retaining the events as opposed to just an aggregate value. But it's limited to retaining windows within a particular, retaining events within say an hourly window or a 2-hour window, whatever your window size you're working with. Here you have things like windowed joins, windowed sort, and so forth. Then finally, we have category 4, which is operators that require to hold on to the entire input effectively to do their job. Things like a full-fledged join or a sort, distinct count, and so forth. These obviously are extraordinarily large in terms of the state requirements and is proportional to the input size. With respect to optional scaling, the point I'm trying to make here is that the first 3 categories are where you get optional scaling. So if you look at all the operators in your job and they all fall in the first 3 categories, and it's a streaming job, then you will get optional scaling. Coming back to the initial slide, the goal of this talk was to explore the possibility of going from these 3 models on the left to the 2 on the right. And that's primarily by evolving streaming into Streaming 2.0, which is a pure streaming model that can accommodate all the offline use cases for which we have traditionally been using batch. And because there is no batch involved in Streaming 2.0, we also don't have the batch streaming unification aspects there. So far, I've been exploring primarily the efficiency and scalability aspects, and now I'm going to talk about more defining what Streaming 2.0 is and what is the evolution needed to get there. The core idea here is to take the strengths of the real-time streaming engines, which is processing unbounded data and event time ordered streams, and combine it with the strengths of the offline streaming engines, which is processing bounded data, and add a few additional features, which then gives us Streaming 2.0. I'll briefly go over these new features listed here. The first one being Kappa Plus architecture. That enables, it's difficult to describe it in very short amount of time. I'll link a presentation in the next slide that goes over that in detail. But at a very simple terms, we have a custom implementation of it here at Uber, which allows us to do streaming mode backfills or effectively any amount of historic data in a single go, both stateful and stateless jobs. The second point there is mixing push and pull based streaming data flow. What that means is maybe some operators in the data flow need to be able to use a pull model instead of push to accept data from upstream sources. So things like hash join operator may decide to first accept all the input from the hash side. And once that's done, then it can switch over. It can basically pull from the other side. The next one is mixing bounded and unbounded processing. this enables many use cases. So, for example, you could have an operator which takes one bounded stream and another unbounded stream, or it could also be in the form of bootstrapping, where you start the job by processing offline data, bounded data, and then you switch over to real-time mode where you're processing unbounded data. And during this switch, it's nice to actually change the concurrency, because offline jobs can work at a much higher level concurrency, and it's not needed in the real-time mode. So elasticity is a useful feature there. And then the ability to mix state backends, so that only the state-heavy backends can use RocksDB, and everything else doesn't need something as heavyweight. So in summary, at a high level, you can think of streaming 2.0 as a merging of two streaming worlds, and with a few additional features. And it's essentially a pure streaming model that can handle all real-time and offline use cases. And it delivers low latency, high throughput, as well as ability to handle large scale. The benefits are more to do with the simplicity of the fewer engines, no need to unify things, and even reduces the scope of unified SQL. So that sort of summarizes what streaming 2.0 is, and what's somewhat needed and what's needed to get there. So with that, I will conclude this talk and open up for questions.